Okay, we're going to continue on here and talk about obviously what we've been talking about, which is chapter 14, part 2. And we got into really buffers last time. So remember, as we talked about, a buffer is a combination of a weak acid and its conjugate base, or the salt of its conjugate base. Or it can be, again, a weak base and the salt of its conjugate acid. And remember that really both of those things are essential to how a buffer works. They both need to be in the solution together. And the reason we need it to be a weak acid or weak base is because they will set up an equilibrium and basically keep in that solution basically your acid part of your buffer and your base part of your buffer. And that's really essential for it being able to do its function. We cannot do a buffer made up of a strong acid or strong base because it will completely dissociate. It will not set up that equilibrium, and you really won't have both of those components in the solution at the same time. You'll either have all base and you'll have all acid, but you won't have both together. So again, a reminder that really a buffer will be able to maintain the pH it's at if it's created correctly, and not see really big jumps in pH when you add additional acid or base to it. You will see probably small little movement of the pH, but again, the pH won't, for example, go from like a pH of 9 all the way down to a pH of 2. You won't have a really big jump in the pH. The way it's really able to do that is because it has both of these in solution. What it really does is it prevents the formation, as we kind of talked about last time, of any free H plus, for example, when you add an acid, and it prevents the formation of any free hydroxide when you add a base. And that's really important because, again, the hydroxide and the H plus concentrations are related to each other. So as one goes up, the other goes down, and obviously vice versa here. And if you're able to basically keep the H plus concentration and the OH minus concentration relatively constant, that will essentially keep your pH relatively constant. That's again why we don't see these really big sort of jumps in it. Buffers are really common ion problems, and that means that we do have some options in terms of how we can solve them. One option is if you could recognize it is a buffer, you could go into obviously the Henderson-Hasselbalch equation where the pKa is equal to negative log of the Ka value. Alternatively, as we also did in a problem, I think, you can choose not to use the Henderson-Hasselbalch equation if you want, and you could actually just do an ice table and it will work out the same way. The importance of if you take more of a ice table approach, as we talked about, we'll just kind of use this guy here as an example. When you do your ice table, you should have an initial concentration of this guy, nothing. And it's really important that you do, again, have the initial concentration on this side. That, again, is going to be your buffer. And if you leave this side out of it, you're really not doing a buffer problem at that point. You're just doing either a weak acid problem or a weak base problem. So, again, that's a very common mistake sometimes people make when they do an ice table rather than the Henderson-Hasselbalch equation. So, I would probably recommend the Henderson-Hasselbalch if you're sure it's a buffer. Maybe less room for error because I've seen a lot of ice tables where this is zeroed out, and again, get the wrong answer in that particular case. Remember, with that being said, that you should not use the Henderson-Hasselbalch in every situation. It is really specifically for any situation that is a buffer, and if it's not a buffer, you should not use that equation. And again, sometimes people get into the habit of, I got two numbers, so I'm just going to put it into this equation and use it. The other thing we talked about and sort of finished up on last time was the idea that when we do add volume to other volumes, like if we had a buffer and we added some acid to it, as we have the volume, the molarity does change for everybody because the total volume of the solution is changing. The thing that doesn't change is moles. So whenever you have a situation like you have a buffer and you want to add something to it, or as we'll talk about when we get into titrations, when you're constantly adding volume or have added volume, it does require you to sort of do that ice table in moles. And usually that first ice table is usually done in moles. And I would say that in most cases, when you're doing an ice table in moles, the other difference is probably 99 times out of 100, you will actually know what the change is. So instead of using X like we do when we do molarity and those type of things, you'll actually know what the change should be. The change should always be usually the smallest number, so you do not end up with a negative number. And we would use actual numbers as we go through our initial change and hit equilibrium. It's important though, once you do get back to the equilibrium for whatever's left over, that you at that point should convert it back to molarity. It's really good practice by using obviously the total volume at that point. So, if I had a beaker of 50 milliliters and I added 10 milliliters of like acid to it, my total volume at that point, right, is 60 milliliters. And that's what I would want to divide everybody by in liters as 0.06 liters, and that takes it back to molarity. Now, the truth is, if you are doing a buffer problem at the end of this ice table, you absolutely can, if you want to, go into the Henderson-Hasselbalch equation at both of those spots with moles, and it will work out okay. Or you could go in with molarity. If you're doing more of an ice table approach, you should definitely use molarity. And some future calculations after you do that first ice table of moles, you usually will need molarity to continue on with the calculation. So it's just really good practice to sort of convert it back to molarity. And then you usually are going to be in the right units for whatever future calculation you need to do. Any questions on that there? All right, so we got to this one, I think, and you're supposed to work it out. So let's go through this one together and see how we did. I don't remember what I gave you last time, but maybe gave you a Ka, but I'll go with the Kb. Why not, for fun? There we go. Let's go with the Kb here, 1.8 times 10 to the minus 5 for NH3. So in this case, we want to calculate the pH of a buffer that's made up of ammonia and ammonium chloride. And this is a buffer. They are related to each other. Once again, this is a weak base. By the way, I know that's a weak base because I just gave myself a Kb value. That's hopefully right. And I know that this over here is actually conjugate acid, and it's really the NH4 plus part here is this conjugate acid. And once again, that is your Bronsted-Lowry definition, basically 1H plus difference between NH3 and NH4 plus. The Cl minus, frankly, is just like a spectator ion, kind of hanging out, floating around, really not doing much in this case. The really buffer components are those two things. So once I recognize that this is a buffer, I could actually calculate, obviously, the opening pH here before I do anything to it. And because I haven't added any volume here, I already have the concentration of each of those guys. So I could actually go right into the Henderson-Hasselbalch equation if I choose. Now, I do have a couple of choices here. I could use that other equation that we talked about, which is like the Henderson-Hasselbalch equation, but does use POH and use the pKb plus the log. Remember, this one is reverse, acid over base. And I could do that because I gave myself a Kb value here. But once again, as I mentioned before, most of the time, like in this problem, we're really looking for pH. So might as well just use the Henderson-Hasselbalch equation, get the pH. I don't have the Ka in this case to get the pKa, but I can do it a couple different ways. I can use Kw and divide that by my Kb, and that would give me 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. And that will give me the Ka value that I probably gave to you last time, which is 5.6 times 10 to the minus 10. I could also, if I really wanted to, get the pKb and then basically subtract it from 14. You will get a slightly different answer if you went that route, but I'm going to go this route. That means my pKa is going to be minus the log of 5.6 times 10 to the minus 10. That's a 925, I hope. Let's see, it's something like that. 925, I think. Yeah. 9.25. So that means in this case, the pH would be equal to 9.25 plus the log. Once again, we want our base, which in this case is the 0.3, divided by our acid, which is the 0.36. And that's going to give us an opening pH here for our buffer of 9.17 in this case. Yeah. And this is a basic buffer, which is why sometimes people would perhaps use that other one. But again, you guys still subtract from 14. It doesn't really matter whichever way you kind of want to do it. Will get you basically the same thing. Question on that there. All right, so now that I have kind of my initial concentration of our molarity or pH, I'll spit that out, one of those guys there. Now my initial pH of my buffer. The next part of the question is we're going to take this buffer and basically add, in this case, some sodium hydroxide to it. So we are going to get a reaction between our buffer and the sodium hydroxide. So when I add my sodium hydroxide here to my buffer, because sodium hydroxide is a base, we would anticipate that it will react with the acid part of the buffer. And in this case, that is our ammonium chloride. And the result of this is a bunch of things, but we will end up with NH3. We will also end up with some water. And for good measure, we'll end up with a little sodium chloride as well. Yeah. Basically, what's happening is this guy is going to send his H plus over here, and that's where the water is going to come from. That's going to leave it as NH3, and the chloride ion floating around will hook up with the sodium ion that's floating around, and you'll get your sodium chloride over there. Any questions on that one there? Because we are adding, in this case, we definitely want to do everybody in this table in moles to begin with. So we got to get the moles of everybody. So initially here for our sodium hydroxide, we are adding, so again, a reminder that basically we have our buffer in here, which is our NH3, our NH4 plus, and some Cl minus, really. And we have basically 80 milliliters of this guy. And we're going to add 20 milliliters of our sodium hydroxide, which is going to go into a swim. So obviously here, to get our moles of sodium hydroxide, we're going to go 0.02 liters times the molarity of it, which is 0.05 moles per liter. That's going to get us 0.02 times 0.05. That's going to give us 0.001 moles for our sodium hydroxide. That 80 milliliters goes for both parts of our buffer components. So to get the moles of the ammonium, we would take 0.08 times 0.36, and that would get us 0.0288 moles. Remember as well, we do have this present here in the buffer. And again, that is 80 milliliters, so 0.08 times 0.3 to get our moles, just like we did with the sodium hydroxide, to get our moles of our ammonia. That's water, which means I'm not going to be concerned with it. And once again, that is a neutral salt that we should know that I'm not going to be concerned with either. So again, I wouldn't throw up some pictures there or numbers that you might use incorrectly. First off, any questions on how I got those numbers there? All right, so since this is a buffer, it should do some buffering action. And like I said before, usually when you do moles, we don't use X's a lot of times, so we already know the change. The change should be, in this case, our sodium hydroxide. And as I mentioned before, always choose the smaller number so you do not end up with a negative number. We are adding on the other side here, so you want to remember to do that. That's going to zero out our sodium hydroxide. That's going to get us here 0.0278 moles. And I'll remember to actually add the other side there. And that's going to give us 0.025 moles of this guy. Now, again, if you're really not sure what's going on at this point, you could always use your ice table to help you maybe figure it out. Basically, what we have left is ammonia. We have ammonium chloride. Again, these things are still related to each other as a buffer. So again, at this point, you still have a buffer left over, which is good because you started with a buffer. As I mentioned as well, at this point, once you do this ice table and moles, it's really good practice just to convert everybody back to molarity. So our total volume at this point is we had 80 milliliters and we added 20 milliliters to it. That gives us a total volume of 100 milliliters in this case. So we're going to basically divide each of these by 0.1 liters, which is our 100 milliliters converted to liters. And that's going to give us really the concentration now of our buffer. It's going to give us 0.25 molar, 0.278 molar here. Again, you do have two options. You could go back to an ice table, or because you hopefully recognize it's still a buffer at this point, you might as well maybe go into the Henderson-Hasselbalch, and that's what I'm going to use. Since it's really the same acid-base type of situation, we got the same pKa value plus the log. Once again, we do want to make sure we get our base on top, which I think should be that guy, 0.25 divided by 0.278, which is our acid. And we will get something maybe. Going to end up with a pH of 9.20 in this case. Any questions on that one there? Does that make sense in this case? It does make sense because we added a base, sodium hydroxide, right? So we should expect the pH to go up. It didn't go up tremendously, which means our buffer is pretty good in this case, right? So we didn't see a giant jump, but at least went in the correct direction. Again, if you did this calculation, you ended up with a pH less than what you started with. You're definitely going in the wrong direction because you're adding base, right? So it shouldn't be going down. Any questions on that one there? All right, why don't you try one more here? We'll do the same buffer, but in this case, we're going to add, let's see here, we're going to add 20 milliliters of 0.1 molar HCl to 120 milliliters of your buffer. So obviously you don't have to do the first part again since we did it in the previous problem. You can just look at the second part here. So let's just do the second part basically. So again, this is our same buffer system. And again, Kb of NH3, 1.8 times 10 to the minus 5. Okay, so let's take a look at it. So again, kind of same buffer system. Really, the first part of the question would be the same. We would end up with the same pH, which I think our opening pH there was 9.17, I think. So in this case, obviously, we're adding some HCl to this buffer system, and we're actually starting with a little bit more of the buffer than we did in the last problem. So again, in this case, we basically have our buffer system that's set up, and we have our in solution NH3 or NH4 plus basically in there. And to this, we're going to add some HCl there. And we got 120 milliliters of this guy. And again, we're going to add, in this case, 20 milliliters here of our HCl. So we're definitely going to get a reaction and we're adding volume. So that definitely means that we want to use moles in our ice table. So we might as well start with calculating moles of everybody. So our HCl moles are going to be 0.02 liters times the molarity, 0.1 moles per liter. And that's going to give us there 0.02 times 0.1, 0.002 moles of HCl. We'll do the same thing for our buffer. Again, that 120 encompasses the volume for both parts of the buffer since they're in the same beaker. So our moles here of, we'll do NH3 first, is going to be 0.12 liters times the molarity, 0.3 moles per liter. And again, that's going to get us there 0.0375 moles of NH3. We'll do lastly here the other one there. So moles of the NH4 plus. Again, this is the only source really of NH4 plus here. And that's going to get us 0.12 liters times our 0.36 moles per liter. And that will get us there 0.12 times 0.36, 0.0432 moles of NH4 plus in this case. Now we got the moles, everybody, we could do our reactions. So in this case, when we add the HCl, it is going to react with the base part of our buffer, which is the NH3. So we'll have a little NH3 action happening here. Again, this is our acid, so it's going to send the H plus over, and we are going to end up with NH4 plus Cl minus. Or you could, if you wanted to, put them together as ammonium chloride, whichever way you want to do it. So initially here, our moles of our HCl 0.002. Our NH3 0.0375, I think it says. And again, very important, we do have some moles of our NH4 plus. Once again, if you leave that as 0, you're really not doing the correct problem here. So 6, there we go. Let's see here. Feel like I hit the wrong number there, huh? 0.036, I think, on that one there. I think. Let's see, NH3, right? Yeah, so NH3 is 0.3, so 0.12 times 0.3. That should be, just double check them both just to make sure here before we continue on. All right, so 0.120 times 0.3 going to give us 0.036, and 0.12 times 0.36. I guess that one was good, I guess. All right, 0.0432. So just that one there didn't look right. There we go. All right, back we go with the right one would be good, 6. All right. Now, I'm not going to, again, in this case, because I know this is a neutral salt, I'm not going to worry about it, so I don't try to use it in the wrong situation. The change here is going to be our HCl we're adding. It is, again, the smaller number. We're going to subtract that along the way here and then add it to this side. That is going to get us here 0 there, 0.036 minus 0.002, 0.034 moles. 0.0432 divided by 0.002, not divided. Hey, I'll get that right. It's Thursday. Plus 0.002. There you go. 0.0452. Again, at this point, if you're not sure what's going on, we can take a look at our ice table, and we do see we still, again, have our buffer left over. So that is, again, the approach that we want to look at. We're going to divide this out by our total volume, which in this case is 120 plus our 20. That's 140 milliliters total volume, 0.140, 0.140 here. gonna get us here, hopefully, some numbers. Looks like 0.243 molar and 0.0452 divided by 0.140. 0.32, I'll call it 3 molar here. Going into our Henderson Hasselbalch, because it's still a buffer, 9.25 on our pKa value, plus the log of our base, which once again is over here is our base. So 0.243 divided by 0.323. Let's see how I did on my made up numbers here. 0.243, 0.323. A little log action, maybe an adding a 9.25. And that's going to give me a 9.13 in terms of my pH. Also does make sense based on where we started at 9.17. We added some acid. The pH went down a little bit. Again, not drastically down or anything like that. Question on that calculation there. All right, so like I said before, you could have, again, just to illustrate we'll go this way maybe. If you wanted to use that previous equation with the POH, since I did write it on this one here, just to show you it here, since we're towards the end here, we'll take a look at it, how you would do it that way. So again, if you chose to kind of do it this equation in this situation, we'll just do the initial guy there. Again, what you would do obviously is you get your pKb value in this case, which would be minus the log of your Kb. And that in this case would be minus the log of 1.8 times 10 to the minus 5. And that is going to get you there a pKb of 4.74. You would then go into your POH would equal 4.74 plus the log. Again, in this case, it is the acid up on top, which means in this case, you would want the 0.36 divided by the 0.30. And that will get you 0.36 divided by 0.3, logging it, plus 4.74. Get you about a 4.82 POH. The pH in this case then would be 14 minus 4.82. And that would actually get you, as you can see, just slightly off 9.18, but basically the same answer, just depending on rounding a little bit how you get there. So again, that would be how you could use that other equation if you chose to do that. But obviously, you could just go right into the pH equation too and get it. Any question on buffers, how to calculate pH or any of that type of stuff? Okay, so we're going to talk then about our next big topic, which is titrations. So let's talk a little bit about titrations here in the last few minutes. Titrations is usually a process that is used when we have a solution of unknown concentration usually, and we use really a standard solution, which is a solution of known concentration. And typically we do titrations, right, using a burette, and we add, right? And here's our burette there, and obviously our solution. And we typically have a solution in, so it really doesn't matter what's up here, but sometimes we'll use something like sodium hydroxide or a base. You could also put the acid up there if you like, and then we'll maybe drop it into our acid down here. Now, we continuously do a titration here, and we continuously usually will titrate to what is known as the equivalence point. And the equivalence point in an acid-base titration is the point where exactly the moles of the acid will equal the moles of the base. It is essentially usually when you do a normal titration, your stopping point. That's usually where you want to end the titration, because that's kind of your end of the reaction. Basically what that means is all your reactants just use each other up. There's nothing left of your reactants at that point. The reaction technically went to completion, and you got your product. The equivalence point shouldn't be confused with what is known as the endpoint in a titration. And the endpoint in a titration is actually the part where you lay up your titration. And hopefully, if you do a good titration, your endpoint and equivalence point should be pretty much the same spot. But if you laid up way early, then you're obviously way far away from the equivalence point. Now, how do we know when to stop? Well, we use an indicator usually. So we typically add indicator to this. And everybody's favorite, right, is phenolphthalein, right? Yeah. Phenolphthalein is what color in acidic solution? It is colorless, yes. And in neutral solution, it is still colorless, by the way. In basic solution, it is pink, yeah. So that's that pink color maybe you did in your titrations there. I'm sure you remember the pink color when you did your titration at Chem 50, right? Maybe you had your instructor just said you should get the lightest, hold up the piece of white paper to it, color of pink that you could get, right? And maybe you had an instructor that said that's too dark pink, you should go do it again. Anyone? Maybe we'll explain why you really probably didn't have to do that, by the way, but why they like to say that. But the reason for that is pH indicators, as we'll talk about, really work over our acid-base indicators, work over actually a pH range. And something like phenolphthalein, for example, works over a range of 8.3 to like 10-ish is really where you kind of see a lot of the action happening. At about 8.3, it's colorless. And then as you gradually go this way, you get your favorite shades of pink, yeah, wherever you may end up. And the reason they usually yell at you that you should have the lightest color of pink that's possible is your equivalence point, for example, in that acetic acid titration you probably did, which is vinegar, is right back in this area around 8 point something, which is actually colorless. So just as soon as it turns, you're probably right there at the equivalence point, and that's why they kind of yell at you to try to get the lightest color pink as possible. And again, we'll explain why you might not have had to redo their titrations, but it probably wouldn't matter too much if you were really careful. So that's why we use these indicators. And obviously, as we'll talk about, when you choose an acid-base indicator, you're obviously looking for a color change to occur near the equivalence point. And not all indicators are the same, as we'll talk about. They do change colors at different pHs. So it does depend on the type of titration you're doing and really what the pH of your equivalence point is as to what is really the best maybe choice of indicator to use. So when we do these titrations, we usually know things. And for example, maybe we know the molarity of the base we're adding. We obviously will know how much base, right? The volume of the base that you added. And maybe the only thing you know about your acid is the volume. And obviously through stoichiometry, right? And titration type problems, you could calculate, for example, the molarity of your unknown solution. That's pretty not too bad, that pink color there, I suppose. And with that being said, we will stop. Yes, it's probably a good stopping point.